Hey, thanks for allowing me to speak to you today. I'm going to try to give you more of a 30,000-foot sort of view of some of the products that we represent and how they can go together and benefit the school systems. One of the products I'll be speaking about today, Ventacity, is an ERV, HRV product, heat recovery ventilator, energy recovery ventilation, very high efficiency. So if you go to Yep, sorry about that. Yep. If you go to ventacity.com, there's a number of case studies on the combination of heat pump technology and high efficiency ventilation. So really the topic today is, as you see, bringing indoor air quality and health to your classroom to help you save money in the long run. Energy obviously leads to saving money. And I want to show you initially, before we get too far into it, just sort of the tools that we have to get you there. So the first slide you see here is, what is VRF? Well, VRF is commonly known as variable refrigerant flow. Anybody familiar with air source heat pump technology at all? Residential or commercial? Okay. So as you probably know, the industry has certainly come a long way over the last 10 years, 15 years for sure. I worked for a mechanical contractor down in Monroe, Connecticut for a long time, selling residential and commercial products. And back then, the heat pump industry was struggling because it was difficult once you got down below 30 degrees Fahrenheit to economically heat with a heat pump. At that point, that balance point, temperature balance point, you'd have to bring on electric heat or electric resistance. And as we all know, straight electric resistance can be expensive. And that was before PV really was on the scene. So in later years now, we have the technology where we can provide a comfortable solution. We can do a great job of zoning, and I'll get into that in a second. There are numerous types of controls that go along with these systems that can allow you to really pinpoint operation of a system on a thermostatic basis. And the compressors today are extremely well equipped to allow for energy savings. They now allow to be able to actually gain and be able to promote heat down to down to minus 15 Fahrenheit. Full capacity on most of these systems is at 0. So without any other source of heat, down to 0 Fahrenheit, you can adequately heat and cool, whether it's a home or a building. In this case, we're talking about schools. So there are two types of heat pump, variable speed type heat pump technology. In the commercial realm, there are heat pumps, and this is a little bit of a line diagram here showing you a heat pump system with your outdoor condensing units, which can be located on the roof, on the ground, as your main source of heat. And the green lines that you see there are refrigeration piping, where you would be able to provide refrigerant to indoor units. And I'll show you an example of all the multiple types of indoor units, one of which you can see in the ceiling here, which is a ceiling cassette. And as I drove up today, I noticed a condensing unit sitting outside, a newer model. So I'm assuming it's connected to that. Heat pumps are historically two-pipe systems. So we're supplying refrigerant to indoor units, indoor fan coils, indoor cassettes, and other different types of indoor units. And then you have a gas or vapor line that's, once that heat is pulled out of that refrigerant, sent back to the condensing unit to again turn it back into a liquid and complete the process in the cycle. And it can be piped very similar to how you would pipe a boiler system. So there are a number of trained contractors throughout the state of Connecticut, and there are a number of different brands. We happen to represent Fujitsu, but there are a number of different brands on the market today, including Mitsubishi, LG, Samsung, Daikin, and others. The second type of system is called heat recovery, and with this you see 3-pipe system instead of 2. What's nice about this type of system is if you take an example of a building that has some east-facing glass, let's say, classrooms, a line of classrooms, and maybe on the other side you have a center hallway, and the other side you have buildings or classrooms facing west. Well, you're going to have different temperature gradients based upon what type of day or what time of day it is. So the sun could be coming up in the east, and all of a sudden you're getting a solar gain. It could be 40 degrees outside, and you have a solar gain that's heating up. You have people, you have children, and you have a solar gain, whereas the other side of the building is not seeing that solar gain, and therefore they may need to be in a heating mode. So a heat pump recovery system will allow to do simultaneous heating and cooling. So this side of the building could be in heat or cooling, and vice versa, the other side could be in the other, all at the same time with their own operating controls to set the temperatures. So although this system is a little more expensive than a standard heat pump, where the other one I showed you, you're either all in heat, the building is all in heat, or all in cooling. Can't be simultaneously doing either one of those. It has to be in one designated call. Yeah.
When it's doing that, is it taking the heat from one and using it to the other?
Yeah, essentially what happens is on the cooling side, when the refrigerant gets into the evaporating units, depending upon what they are, whether they're those or ducted units, they're rejecting heat back to the condensing unit. Well, instead of doing that, that rejected heat or vapor goes back into a branch box, which is then diverted over to the heating side. So you're actually, in a sense, getting free heating in an application like that, because you're reusing what normally would go back to the condensing unit and be exhausted out. If you have a central air conditioning unit at your house and you're running it in the summertime, put your hand on the outdoor condensing unit and feel that heat coming off of there. Well, that heat can be reused onto the heating side of this type of a system. So again, it's an energy saver, more expensive upfront costs, but certainly pays for itself well within the life of the product. The indoor units that can be coupled with these units are varied. You can see a number of units here, the top area being the ducted type units, and those are sizes in thousands of BTUs. So the top left model 4, 7, 9, 12, 14, 18, that would be 4,000, 7,000, 9,000, and so forth. As you can see, there's some larger units up to 96,000 BTUs, and again, commercial applications. The smaller units that have the 4 next to them, very much used in passive house applications, lead and passive house applications, because in those applications, the heating and cooling requirements are so low that those units actually start at 4,000 BTUs and turn down to 800. So you can really provide the right amount of heating and cooling to a space without overheating or overcooling, or using units that are too large and taking up more energy than you need. But as you can see, a number of different units there, the ceiling cassettes like we have here, wall-mounted units. If anybody has a ductless type system in their house, they may have wall-mount units with remote controls to operate them. You can do the same with this, or wired controls, which I'll show in a second. And ducted units at the top, and also floor and ceiling models. So there's a lot of different choices depending upon the application and the design of that building and that room. Lastly, Ventacity is the ERV, HRV line, energy recovery ventilator or heat recovery ventilator. The difference really between the two and how you choose which one would be right for the application really depends upon the occupancy and also whether or not you need to recover humidity. The heat exchangers in these units are a little bit different between the ERV and the HRV. And I want to preface you to understand that, because as we get into further slides, you'll understand sort of the differences. But the ERV, anybody familiar with the Gore-Tex material? Probably have seen it in jackets and things like that. Okay, so Gore-Tex, the ERVs have the energy core in the middle actually uses a material like that. It is not Gore-Tex, but it's similar, so it allows for small molecules of moisture to get through from one side of the unit to the other, but doesn't allow for odors and things like that to get through. So the energy recovery ventilators in this climate are probably more prevalent just because of the temperature gradient that we have here in Connecticut. When you get down south, you really don't want as much moisture to be transferring back in. You want to get rid of as much as you can. The heat recovery ventilator does just that. It doesn't transfer moisture. But as you can see, the way these work is on the top left, you see the blue ribbon, if you will, coming in. It takes a right turn, comes down through the energy core. It will then get down to the bottom there, take a right, and come into the building. On the left is where we would exhaust stale air, if you will, up and through that core. Now, those streams do not touch each other. Okay, you've got airflow coming in from outside and you've got airflow going out, and as that 70-degree air in the wintertime is passing through that core and that 30-degree air coming in is passing inside of that core, it's gaining its energy. There's an energy transfer that takes place, and that HRV is an aluminum plated type material, and it will transfer that energy so that by the time that 30-degree air comes in and gets into the building, it's in the 60, 65, 67 degree area. So you've used all of that heat and energy that you would normally have just sent outside to transfer into the oncoming stream of air. And it can be done very well with high efficiency. There's a lot of ventilation equipment on the market today. It's important with what you're going to see today that you choose a very high efficiency unit in order to do that, okay? Because otherwise, if you don't, you're going to be adding more and more HVAC to make up the difference in temperature. And we'll get into some slides that show that and explain that a little better. It's just the internal workings of what you have, controls, heat exchanger design, ECM technology, and the fans. Yes?
And in a school, this is an absolute necessity. If you're trying to reach net zero, an absolute necessity because schools have very high ventilation requirements.
Yeah, we're
very high population.
Yeah, you'll see some studies on that exactly. And then there's numerous controls that can put both systems together. And you can do it from you can send signals to a contractor to let him know that there's a problem with a unit, so that contractor, before he even steps out of his office to go to see what's going on, will know exactly what's happening, and have parts available and so forth, so it becomes a quicker service call, if you will, if necessary. So, what we're here for, can we electrify our schools? Well, we know, and just what you said, ventilation is important. Most of the systems that are on schools today, the older systems, are doing it very ineffectively, the way that they're bringing in ventilation air. It's costing a lot of money to do that. Also, most of them have some type of a fossil fuel base or backup in order to do that, right? So if it's a gas-fired rooftop unit, if it's a boiler, if it's a chiller, most of the time those units are fossil fuel operated. And with this technology now, because again, we can be heating down to 0 Fahrenheit, and by the way, the units don't turn off until it's around -23. It's a refrigerant pressure reason for that. So these units can run down and they won't shut off. So if we ever see -23 here, we're okay. So buildings use about 40% of total energy in North America. And that's a statistic that has been written about. In New York City, it's higher. It's about 70%. Outdoor air is extremely important. Obviously, we're talking about increasing the importance of it. LEED points are available. We're seeing passive house school and LEED type projects happening all the time. The more the ventilation, the higher the efficiency of the HVAC equipment, LEED points are available for that. of all of that, outside air ventilation accounts to 30 to 40% of the building energy usage. And that's not just, that's a combination of the fans and what it takes to temper the air. And the next slide will show a little bit more of what we're talking about as I get into this. So that means that outdoor air in buildings accounts for 12 to 16% of all energy use in North America. Nobody really thinks about that, about ventilation and how you move fresh air from outside into the building. But that's a lot of energy being used in order to do that. There's been a number of studies. I picked 3 of them as far as ventilation, and you guys can tell me because I'm not as familiar with it. But I know in California that those schools get monies based upon how many kids are in those seats. So the more kids are attending school, the more money that school district is going to get. So that's an important part of all this. Just by increasing a classroom's outdoor air from a California average of around 8.5 CFM, or cubic feet per minute of air per student, to the state standard of 15 would decrease illness by 3.4%. Well, you take the state of California, 3.4% is a big number. So just by doing that with proper ventilation, you're looking at some significant savings. In Texas, the medium CO2 levels were 28% higher than the ASHRAE limit. Okay, so that's another thing, is CO2 levels. And in Washington and Idaho, there was a study of 1,000 parts per million increase in CO2 was associated with a 10 to 20% increase in student absence. I don't know about you, I've been in environments where, you know, you're studying, a library situation, ventilation air is not so good. After 2 or 3 hours of studying for finals, yeah, we've all been there. All of a sudden your eyes get a little tired and your head starts to drop. Yes?
All this is very important in terms of the ongoing asthma epidemic among children in this country, and that this serves to reduce the number of asthma attacks, increase ventilation and lower contaminants in buildings.
Yeah, absolutely. And the air on these units is obviously filtered as well, so that incoming air goes through a significant filtration system. So why should we ventilate? Well, better ventilation means better performance. There's been, again, a number of studies. Harvard did one looking at a 400 parts per million increase in CO2 associated with a 21% decrease in cognitive function scores. There was a study in the southwestern United States, a number of states that put this study together with 70 schools, and mathematics scores were increased by 0.5% per 2 CFM increase in ventilation. So as you're increasing the ventilation and increasing fresh air into that space, the cognitive ability is raised, okay? Math and reading scores were 14% higher when we increased the ventilation rates, greater than 10 CFM a student compared to less than 5. So all of these are studies that have been done, and you know, they're available for you to view as well. You'll have this PowerPoint to look them up, but there are numerous studies, and I picked these 3 because they really jumped out. Healthier conditions, we just mentioned the asthma thing, right? So just by increasing ventilation from 8 to 15, reduce sickness and absenteeism by 4%. And that, again, you take states like Connecticut or Massachusetts or bigger states, that's quite a bit of 4% is a big number.
Sorry, when you say increase from 8 to 15, what are the units on that? What is that?
Cubic feet per minute of airflow. Yep. Yep. And surprising results. Harvard-Syracuse study of cognitive function in office workers. Green days, 61% better. Green plus days, by bringing even more ventilation air into the space, 101% better. And the most affected categories, which, again, these are the most important places that these people work, critical or crisis response, information usage, and strategy. One place I always like to pick on is air traffic controllers. I wonder what type of ventilation is in some of those buildings. I mean, think about those people sitting for day, hour upon hour, monitoring the flights that are going all around the country and all around the world. Those are the type of environments where this type of thing is critical, as well as the White House. I won't get into that. So ventilation is really buried in the HVAC numbers. Everybody knows heating and air conditioning. Ventilation is kind of the lost letter in this, unfortunately, and we're trying to change that, and we're going to try to show you, I'm going to try to show you how we can do that. What rooftop units, which is a normal type of an application, and a lot of the schools that you work in probably have rooftop units, gas-fired rooftop units, or gas-electric rooftop units, they can't allow for demand control, meaning you can't set those things in order to bring in the exact amount of airflow that you need based upon the environment that you're working in. The other thing is when you have a rooftop unit, that's bringing in whatever the temperature air is outside, and therefore you have to now post-heat and post-cool that before that air gets dropped into the space. It's a lot of energy involved in doing that. With proper ventilation, we can cut the energy loads and many times in half. And therefore, what does that do? Well, that allows for less PV. So those upfront costs for PV, we can lower the amount of PV needed because we're lowering the amount of heating and air conditioning that's needed due to the fact that we're recovering with these energy recovery ventilators anywhere from, in this climate, anywhere from 82, 83% up to 90% efficient. So of that 70-degree air that's coming out of the space, we're able to recover 85 to 90% of that energy or that heat and put it back into the building. Therefore, you don't need as much HVAC in order to post-heat it or post-cool it to the 70 degrees that you want inside when that air comes back in. Last thing you need is to have something coming in at 30, 20, 25, 30 degrees, and it's 45 or 50 degrees coming out of the registers. That's not going to work. People will notice right away. The other thing is fan usage. Fans in these units. The nice thing about high efficiency ventilation and also the fans that are in the HVAC variable refrigerant flow type systems are all ECM Motor Technology. So we're converting AC to DC. That power is a lot less than you're going to find with a typical PSC type motor that's on most equipment in our schools. This is a nice example of high efficiency ventilation versus some ventilation that's not so good. Okay? Both of these are going to be better than a rooftop unit, but in this particular case, I like to use this example because on the left I show a heat recovery ventilator that's 65% efficient versus a heat recovery ventilator at 85% efficient. Now, most of our competitors, unfortunately, are in that 65 to 70, 72% range. Fortunately for us, we rep that Ventacity product that is consistently anywhere from 82 to 90%, at least in the climate that we're in here. So what I used here is an example of 40-degree outdoor air and a set point of 70 degrees inside. So we're trying to maintain 70 degrees in a classroom situation, and it's 40 degrees outside. So we're bringing 40-degree air in, and if that energy or heat recovery ventilator can only recover at 65% efficiency, we're looking at a temperature that's going to be coming out of the ventilation ducts at around 59.5 or around 60 degrees Fahrenheit. At 85%, those same conditions, because of the efficiency of that unit, we can now be at around 66 degrees. Quite a bit difference. What does that mean? Well, in BTUs, it's a lot. You're looking at a difference of more than double in order to provide the energy needed on an energy recovery ventilator that's 65% efficient versus one that's 85. Take that, and that's based on 500 CFM. Take that and put, and a 500 CFM unit is normally, that ventilation product is normally a classroom or library type unit. So if you take and look at the amount of CFM you need for a classroom and multiply that out, that's quite a bit of BTUs. Cost per watt is exceptional as well when you have ECM technology and the tempering air and the fan efficiencies, and you can see a yearly operating cost of some competitors of ours versus one that's 85% efficient. That's the counterflow heat exchanger we talked about, and basically the slide is showing how you're bringing in 35 degree Fahrenheit air going through that core. It's picking up the 70 degree air that's coming back. It's transferring that energy and providing 66 degrees into the space. Versus an economizer, which is on a rooftop unit. Again, the economizer will open and allow for fresh air to come in, but again, because it's not going through a ventilation system like this, it's going right into the ductwork and you have to post-heat and post-cool that. So you're using a lot of energy in order to do that. Nice thing about high efficiency ventilation is it allows for a smart ventilation system. It allows that you can do demand control with it, meaning that you can set this up on temperature, you can set this up on CO2 levels, so it'll monitor CO2 and vary its amount of airflow into a space based upon who's in that classroom and what they're doing. You can also do it based upon humidity as well. So depending upon the application that you have in the room that you're in, you have all those available. The fan motors on these units are ECM technology, again, so we're talking very high efficiency. And this is a picture of a classroom unit, which would actually go in the classroom and free blow air into the space and come back around and up into the unit as a return. You're bringing fresh air in and you're exhausting, so that unit's going to be at the end of a classroom. Skip through some of this. Smart controls, obviously we talked about that, that you can do a lot of things with the control packages that are available today for control. And there's a number of types of controls out there that also will monitor both the HVAC equipment and the ERV and HRV. I'm going to skip through this, but the solutions, this gives you an idea of lower first cost. If you're looking for applications and you have applications where you need equipment, there's a number of units here that we compare versus VRF, ERV on the right. These numbers are real numbers based upon applications that we've tracked. And you've got a CB is a chiller boiler, VAV is a rooftop unit, and VRF and ERV is what we're talking about here today. Yearly energy savings is great, obviously, because we're consuming less. No gas, fossil fuels goes away. So again, you're eliminating fossil fuels altogether with this type of a combination. And you've got total reductions of the VRF ventilation system versus the best option in a 2016 study. First cost reduction of over $5 million. And this we see all the time. The upfront cost of the equipment, the operating cost of the equipment, overall annual savings, that number is something we see all the time. And that's what the unit would look like for a classroom. Again, hanging on and that runs on top speed, 500 CFM at 35 decibels. That's like somebody, taking some leaves blowing across the ground or paper being put away. Yes?
Do you make these ever with chilled beams or chilled ceilings?
No, in fact, that CB that's what that was, a chiller boiler with chill beam application. This is airflow. This is moving air. And this is a job in Maine, and this is what we're replacing, a train unit up there that actually has a heat coil in it, and they're bringing fresh air directly from outside with a heating coil with a fossil fuel boiler in order to bring that temperature from 0 in Maine into a classroom up to something that feels comfortable to those students. A lot of energy being used in order to do that, besides the fans that are moving the air as well as the coil that's in that and the fossil fuel to do that. Kind of gives you a picture of what was there. That's what the outside looks in. One is bringing air in, one is exhausting air out. I know this was a quick 30-minute presentation. It's tough to dive into the nuts and bolts of this, but certainly you'll have this presentation. If you need to reach me, I'd be happy to kind of do a deeper dive for you at some future date. Any questions? Yes?
So the ventilation is not completely separate from the heating?
Ventilation is completely separate from the heating, decoupled.
Okay, and cooling for that matter.
Yes, correct. Not into the same ductwork.
A unit like this in the ceiling and a ventilator?
You'd have some registers along certain areas of the space that would be bringing in just the fresh air and exhausting the stale air. Yeah. Yes?
One thing I'd like to point out is that if you have a chilled beam system, it's hydronic, and the ventilation is totally separated from the heating and cooling as well.
Yeah.
Same type of system. I've put these systems in, and they're very simple to put in, they're very effective. The one problem you have that I've seen is that they're difficult to put into a school where you have a large volume area, like a gym or a cafeteria, because you can't get enough circulation of the heating air. We looked at them in Brookfield. At first they look beautiful, but it runs into some problems we're not looking at right now.
Yeah, design is very critical. Where those units go, obviously the amount of airflow and CFM that you need in order to distribute that air. So there's a number of different ways you can do
We
that.
installed them in a big military training center, and then they work great.
Yeah.
School, I haven't seen them installed in school.
Right.
So part of your savings would be a lot less, I mean, ductwork has got to be more expensive than pipes, right?
Well, in most cases, if you have rooftop units already, we can actually reuse that duct system
For the pipes.
for the ventilation.
So I'm talking about like in a new school building.
Yep. Yeah, it depends. I mean, you're going to have ductwork with the HRV, ERV, absolutely. You need to move that air into spaces. The rest of it is refrigerant piping on the HVAC side.
You save a lot of ceiling space, because you don't have to run all that ductwork through the ceiling, only the ventilation.
Right.
The heating and cooling ductwork is definitely save space in the ceiling.
Right. Yes.
What's the minimum scale that this works at?
Minimum scale?
How much square footage do you need in order to bother the
Good question. I mean, it can be done in, you can put a ventilation system in one classroom if you want to. And the same thing with HVAC. I mean, the systems are from 12,000 BTUs up to, 24 tons. I mean, we're talking 250,000 BTUs, and you can put up to, hundreds of indoor units off of the outdoor condensing units. So really, it can be as small as a one small office up to, a large school or office building. Yes.
Schools are a peculiar occupancy, say, compared to almost anything else like an office building, because they have large common spaces that aren't used all the time.
Mhm.
I'm thinking of auditoriums, cafeterias, gymnasiums, maybe a library. So let's say a school has 500 students in it, and they're in their classrooms. You'd want to supply that ventilation to the classroom.
Sure.
But you wouldn't want to supply it to the unoccupied rooms. And so it's really important that you use smart controls to control the ventilation, because it is always expensive to use. So you often connect with the lights, and the lights are on a motion sensor, so when they shut off, the ventilation also shuts off in that space.
You could also do it by occupancy as well and demand control. So
A school with 500 students, you don't want to ventilate it as if there were 2,500 students.
correct.
Because they're not all, you have to figure out where they are and ventilate there.
And that's the advantage of these type of units, because they all are variable speed, and based upon whatever's happening, it's going to vary that fan to provide that amount of ventilation and/or HVAC based upon what the need is. So, yes.
So what is the solution for those larger gym spaces?
Say again. I'm sorry.
What is the solution for those gym spaces, those large open spaces?
In a situation like that, a gym, it's going to require a lot of CFM when there are people in there. So we would, in that case, we would design a system just for that gym. as far as ventilation goes, because of the requirement that when there's 100 kids in there, you need to have a certain amount of airflow. So it would be on its own system, and it would just be operated on demand control, whether that's CO2 or temperature, whichever way we wanted to do that. Yes?
Once the system's installed, is there a component of education of not only the school maintenance folks, but also maybe the students, or at the very least, the local officials?
We love to do that. That's a vital part of all of this. It's education and understanding how the system works compared to what was there in the past or what they've been used to in the past. So yeah, that's something that we do as the rep, along with our manufacturing partners daily when those systems go in. Yes. Great. Well, thank you. I appreciate the time and the opportunity. Have a good afternoon.